Okay, so in the last class we were talking about these equilibrium expressions and the value k. So let's think about just a random equilibrium problem. So maybe we have A reacts to form B, and then B can go in reverse to form A. So we know this problem has an equilibrium expression because we have a reaction that is reversible. And then K is equal to, and I'm going to set K over here so I can focus on the new thing in a minute. So K is equal to the concentration of products divided by the concentration of the reactants. So now K is the concentration of products to reactants at equilibrium. So at equilibrium, and I usually abbreviate that EQ, at equilibrium, K is equal to the concentration of products divided by the concentration of a reactants. So it just tells us how much products versus reactants we have at an equilibrium. Okay, now what about if we're not at equilibrium? Like right now, what's going on? So right now, if we ever want to know what's going on right now, we have a different variable called Q. And Q is actually the same expression as K. It's still the concentration of products divided by the concentration of reactants. It's just telling us what we have right now, which could be at equilibrium, but oftentimes not. So now if we look back over here at our reaction, Q is also equal to the concentration of products divided by the concentration of reactants. Now let's say, what if Q were 1 and K was 1? Well, I guess these two values are equal to one another, so that tells me that right now we are at equilibrium. We're at the equilibrium concentrations when these values are equal. Now, what if Q was 1 and K was 10? I think it helps if you kind of envision these as the ratios. So 1 is really like 1 over 1, and 10 is really like 10 over 1. So it looks like the reactants are equal, but the equilibrium needs to have more products. So whenever one value is higher, I always write an arrow towards that larger value. And this means that this reaction is going to need to favor the forward reaction to make a bunch more product. So this reaction right now is at a 1-to-1 ratio, and it needs to be at a 10-to-1 ratio, so it will favor the forward reaction. Now the reverse reaction is probably still going on, but just more of the forward one. And now the final situation, what if Q were 10 and K was 1? So now again, to kind of envision these as ratios, let's say 10 is like 10 over 1 and K is like 1 over 1. So now it looks like we have, way too much product and we want the product to go down. If you want the product to go down, now again, I'm just going to always draw my arrow towards that greater value. That means we need to make more reactants and take the products away. So this reaction right now would favor the reverse reaction to kind of get that Q value down closer to that 1-to-1 ratio. Okay, so let's take a minute, pause the video, and let's try and answer questions 1, 2, and 3. So just pause the video and then try and answer these three. Let's check what we got here. Okay, so the difference between Q and KEQ is Q is the concentration of products over reactants right now at any time, could be at equilibrium but could not be, and KEQ is the concentration of products over reactants at equilibrium. What happens when Q is greater than K? You go to the bigger value. It's going to favor the reverse reaction. What happens when K is bigger than Q? It's going to go towards that greater value, and it's going to favor the forward reaction. The goal of all this stuff is to try and reach that equilibrium value. Now let's try and apply this kind of conceptual information to a problem, a little more quantitative in nature. So down here we have 0.035 moles of SO2 reacting with 0.08 moles of, 0.035 moles of SO2, 0.5 moles of SO2-Cl2, and 0.08 moles of Cl2. They're combined in an evacuated 5-liter flask and heated to 100 degrees Celsius. Now temperature, although it does affect equilibrium values and the K values, it doesn't change the math at all. So let's just get rid of this 100 degrees Celsius. We don't need to really care about that. Okay, now looking, we know this is an equilibrium expression because we have both arrows going forward and backwards. so it's asking what is the Q. Now Q still equals concentration of products divided by the concentration of reactants. Now this would equal the concentration of SO2 raised to the first power times the concentration of Cl2 raised to the first power, because there's 1-to-1 ratios right here. And then we would divide all of that by the concentration of SO2 Cl2, again raised to the first power. So this is kind of setting up my Q expression. Okay, now we got to plug in the numbers in here. So now, like I like to do in class, could we just put in 0.35, 0.5, and 0.08 into these little expressions here? Just think about that for a second. Think about what these brackets mean. It's a pretty sweet Band-Aid, isn't it? Insects, I guess, this time. Okay, so we can't use these values up here because these are moles and not concentrations. So again, if we want to get concentrations in here, we need to do moles per liter. So let's set these up. So SO2, it said, was 0.035. So I'm going to do 0.035 divided by 5. And I get 0.007 molar. Okay, my Cl2 concentration was 0.08. So 0.08 divided by 5, and we get 0.016 molar. And we're going to divide all of that by 0.5 moles divided by 5 liters, which is 0.1. So now we do a 0.007, and we multiply, make sure we're not adding here, by 0.016. And then we divide all of that by 0.1, and we get Q equals 1.12 times 10 to the negative third. Now that is just 0.00112. And now let's think about K. It said over here in the problem that K is 0.07, so Q is this value, and K is 0.078. So now if we want to know what's going to happen, or which direction will the reaction proceed in order to establish equilibrium, and I shouldn't say which will proceed in, but which one would be more favored. Because remember, equilibrium is a dynamic process, which means that even when it looks as if the reaction is over, things are still going on. There's just the rates are equal. So it looks to me like 0.078 is greater than 0.00112. We're always going to go towards that greater value. So this reaction would favor the forward reaction and be shifting more to the right. Okay, now we're going to use this concept of Q and K, and we're going to learn about ice tables next to find out if we have initial concentrations, how we can calculate what the equilibrium concentrations will be. So now try those 3 ice problems. Good luck.